Here we go. Let's see how long this thing's gonna last. One of these days I'm gonna rig up a better camera system. Alright, so in the simulation, grown-up talking. In the simulation you learned about excess and limiting. The limiting thing is what determines how much product you can make. Hopefully you've turned your simulation in the box, because it is due 5 minutes ago. So when you do, when you have two reactants, you need to make two T-charts. Whichever T-chart gives you the less product, that's the limiting reactant. When you want to figure out how much excess reactant is left over, you do a third T-chart to figure out how much excess you actually had to use. Okay, this is in the simulation. Hopefully you figured it out. We've been doing it for the last, well, if you're a sophomore, 1 day. If you're a junior, 2 days. So the excess reactant was left over, the limiting reactant gets used up. How much limiting reactant is left over at the end of the reaction? 0. Okay? The limiting reactant is entirely used up. Okay? And understand, I mentioned this last time, molecules need to be whole numbers. You can have extra molecules. Moles, however, can be fractions. Because moles are like dozens. You can go to Krispy Kreme and order a half a dozen. You can't go to Krispy Kreme and order half a donut. I have. Okay, well, they looked at you funny, and then they took pity on you and gave you a half a donut. Like, this one dropped on the floor, you can have it. Okay. So we've done these practices already. Now, where we're going today is mass to mass. Mass of A to mass of B. We need to remind ourselves of very, very important rules. Is there any conversion that goes from mass of chemical A to mass of chemical B? There is no conversion. You cannot go from grams of something to moles of something else, from grams of something to grams of something else. You can't do it. There's only one way to change chemicals. And what is that way? Mole. The only way. There's only one. There's only way you can change chemicals from mole of A to mole of B. That's the only way. Mole ratio is the only way you can change chemicals. How can you change chemicals? Use the mole ratio. Can you use anything but the mole ratio to change chemicals? Is there any gram of A to mole of B? Okay. Those who aren't paying attention, pay attention. Because even though a few of you are saying it, I'm going to walk around the room and I'm going to be like, I just went from mole of A to gram of B because I want to do it in one step. Can't do it. Alright. We're going to do the best T-charts. Big, beautiful T-charts. Big T-charts. Big, beautiful T-charts. Each. It's going to be a huge T-chart. We're going to compete with China. Okay. So before we get to mass, which is where we're going to be in about a half an hour, we're going to start with mole mass. It's not as valuable in a practical sense, but you still need to know how to do it. So let's go ahead and do an example exercise together. That favorite reaction we do over and over and over again is if you take hydrogen gas and you react with oxygen gas, it's going to blow up and make water vapor. Yes. Okay. Now, is this a balanced chemical reaction? No, it's not. If you were to balance it, what would you do? 2, 1, 2? Put a 2 in front of the hydrogen, a 1 there, and a 2 there. So Tony seems to think that's balanced. It seems he's right. 2 by 2 is 4. 2 by 2 is 4 hydrogens. 1 by 2 is 2 oxygens. 2 by 1 is 2 oxygens, and it's balanced. Okay, so the exercise says this. How many moles of O2 with plenty of hydrogen are required to produce 12 grams of water? Now, this wants moles of oxygen. We're given grams of water. Can we do this in one step? No, we cannot. So, let's make our tea. Make our tea. And what goes right here? Nothing. How many boxes are every conversion? 2 boxes. Every conversion requires a top box and a bottom box. Every conversion requires a top box and a bottom box. So can you put a conversion into the first box?
No.
No. You never start with conversions. I was seeing that a lot in the simulation as you guys were going through it. You're like, let's throw a conversion up there. You can't. You cannot start with conversion. But what we can start with, what should I put right here? What's my starting value?
12 grams of water.
Yeah, 12 grams of water. How many things go in each box? 3. Tres. Trois. Trois. 3 things in each box. A number, a unit, and a label. Hey, cool. So we're off to a good start. What's my next step?
How to ride bike.
Yeah. Whatever unit I have right here is going to come down here. So I've got grams of hydrogen. I'm going to move down grams of hydrogen. Should I move down the number?
No.
No, I should not. Okay. We're not going to move down the number, just the unit and label. Now we got grams of hydrogen. It would be pretty cool if I could go from grams of hydrogen to moles of oxygen, but I can't. There's only one way to change chemicals, and that is the what? The mole ratio. So I have to get my grams of water into moles of water. Why do I have to convert my grams of water to moles of water? Exactly. The mole ratio only works with moles. So I want to get my chemical to moles of something else. The only way I can change to something else is a mole ratio. So that's what Michael's telling Gavin right now. Wait, this is how it works. Kind of like, so, where does a gram per mole ratio come from? The periodic table. Hydrogen is a mass of 1. So this is 1 plus 1 plus 16. 1 plus 1 plus 16 is usually 18.
Usually though. Wait, but so in this case, is it still 18?
Yeah, in this case it's still 18. So yeah, 1 plus 1 plus 16 is, or 1 plus 1 plus 16 is still 18. So that means for every 1 mole of water, we're going to have 16 or 18 grams of water. Is it always the number of gram per 1 mole? Always?
No.
Yes.
Oh, it is.
Yeah, it's always a number of gram per 1 mole. When you're looking at that little stick in your car that goes up and down, it's always number of miles per 1 hour. Okay? We're like, I'm driving along doing 35 miles per 1 hour. Uh-oh, the needle moved. Now I'm probably doing 45 miles per 4 hours. No, it's still per 1. Okay. So gram per mole is always gram per 1 mole. 18 gram per 1 mole. Hey, cool. So my unit now is moles of H2O. I like to write my goal unit somewhere over here to give me a reference. And the goal is mole of O2 with a question mark. So I can put my goal unit up there somewhere just letting it have a reference like I'm shooting for. So I got moles of H2O. I want moles of O2. Am I done? No. Make another box. Bring down my previous unit, mole H2O. And now I have mole H2O. Is there a conversion between moles of H2O and moles of oxygen?
Yes.
Yes, there is. Where does that conversion come from? Yeah, the mole ratio from the balanced chemical equation. And it looks like oxygen should get a what? 1. A 1. And water should get a 2. Okay, question? No questions? Okay. Question? The 2 came from the coefficient in front of the water. So any mole ratio will always be the coefficient from the balanced chemical equation. In this case, 1 to 2. Okay, give me a thumbs up, you're with me. Damn, most of them said like 80% participation. Okay, if you don't understand, wave your hand around.
Yeah, you
Okay,
can't
moving
see.
on.
That would be 82%.
Cool, yeah.
Damn.
All right, so the unit I have is moles O2. Is that my goal?
Yes.
And when I get my goal unit, I get to make these 2 little lines like that. And the math becomes 12 times 1 times 1. This is the last time I'm going to put times 1 times 1. Okay? I'm not going to write ones anymore in the math. I'm just going to ignore them. So this is the last time. I'm writing it so you can see how the breakdown works. Over 18 times 2 And that's going to be so many equals moles O2. So bang on your calculator to find out what that is. 0.33? All right, listen carefully. If you are one of the people who quite innocently didn't get 0.33, what you did was this. You did 12 divided by 18 times 2. I don't do that. Okay. So if you like to put everything in one string, then make the 18 times 2 in parentheses. Okay. So folks will be like, I got 1.3. You did because you did 12 divided by 18 times 2. You got to be things, algebra. Your calculator's a moron. Just realize your calculator's a very hardworking moron. It works very hard, but it can't think for you. It can only do what you punch in. All right, how are we doing? Okay, give me a thumbs up if you got this. All right, next one. The difficulty is about to ramp up a little bit. Yeah, it's proud mode. We're in proud mode now. Okay, but not critical mode. We're just in proud mode. If you react 3.5 moles of hydrochloric acid with 2.3 moles of zinc, how many grams of zinc chloride will you produce?
7.
So let's write our chemical reaction 7, just right off the top of your head. Wow. So this is the reaction we did where we took the hydrochloric acid and we reacted it with some zinc and we made some hydrogen gas. We do this a lot. And then some zinc chloride. Okay. That was the reaction we used. Yes?
If we get questions like this, it's going to give us the equation, right?
Excellent question. Not always.
Oh.
So if, guys, listen carefully. There's a reason we did balancing chemical reactions before stoichiometry. If the equation is complex or you've never seen it before, it will be given to you. If it's a simple equation you've seen before, sodium and chlorine making sodium chloride, hydrogen and oxygen making water, that kind of thing, then you're going to have to do it yourself. Okay? So the good news is, easy stuff, you'll do it yourself. Complex stuff, it'll be given to you. All right, so is this a balanced chemical equation?
No.
Yeah.
Not yet. If you were to balance it, how would you balance it?
2, 1, 1, 1, 2.
2, 1, 1, 2? 2, 1, 1, 2.
I wrote it. Yeah.
All right. Let's see if we're right.
I wrote it in a different
2 hydrogens, 2 hydrogens, 2 chlorines, 2 chlorines, 1 zinc, 1 zinc. Hey, perfect. All right. So, how would we start this equation, or how would we start this exercise?
HCl. Oh, we have to do 2 T-charts to find out which one has the more problem.
Oh, 10 points to Gryffindor. Yeah. We have 2 reactants. Since we have 2 reactants, we need to make 2 T-charts. We don't know which one's the limiting reactant. We've got 3.5 moles of hydrogen chloride, and we've got 2.3 moles of zinc. Only one of them can be limiting. So we're going to make 2 T-charts. One of them we're going to start with 3.5 moles of HCl. The other, we're going to start with 2.3 moles of zinc. And this is where you see how you're doing. So go ahead and work these out on your own. I'm going to be a minute or 2 behind you. Again, remember, practice makes better.
Practice makes better.
Practice makes better.
No one's perfect.
No, we got. Well,
Except Mr. Byers.
except Jesus, but he can't dunk because he's in heaven.
I feel like there's basketball courts in heaven. I mean, if Snoop Dogg said there's weed in heaven, there must be basketball court in heaven. So,
Well, don't be sorry. Someone's going to have to make my burritos and hamburgers and clean the streets and pick up my garbage. If that's your goal, then by all means, don't.
you know what Jacob, Mr. Byers, you know what Jacob Sanford told me? He goes, I want to be a mailman when I get older.
Cool.
This was like a week ago.
Does he realize he'll have to do math?
Probably not.
Probably not. Yeah. There is some math involved in delivering mail. But hey, that's a noble profession.
People are.
You gotta get the ACL to molds and do a mole ratio.
I want to do the freaking newspaper thing.
Don't worry about it. Yeah, because hydrogen is going to be a product that we don't care about. We're only looking at the product of zinc chloride.
Okay. So, would you put 2 moles ratios?
In the mole to mole,
Yeah.
you would.
Why is it 1 mole ratio?
Oh, it's not.
Oh.
Thank goodness you're here.
Yes.
Where would I be without you?
Even my mama knows. Dude, I don't even get that. How does this string just go straight?
I didn't think that. What's the math?
Oh shoot. The math on that is a Duracell battery.
2 moles.
Whoa. Is it hard? Oh god!
Keep going, Byers. Next box.
Oh my god, it's so good. Oh my gosh. I can literally. Dude, I knew it.
Does your word look like mine?
No.
Well, now it
Okay.
does.
Oh, because you have one more box? Does the first 2 boxes of your word look like mine? Okay. If you don't understand why those numbers are the way they are, put your hand up and wave it around. All right, so you've got 2 reactants, 3.5 moles of HCl and 2.3 moles of zinc. We need to convert our reactants to our product of zinc chloride. And there's only one way to do that, and that is with a mole ratio. So I'm going to bring down my moles of hydrogen chloride, and I'm going to convert to moles of zinc chloride. Bring down my moles of zinc, and convert to moles of zinc chloride. In both cases, the numbers are coming from the balanced chemical equation. Hydrogen chloride gets a 2, zinc chloride gets a 1. Zinc gets a 1, zinc chloride gets a 1. Now once I have my moles of zinc chloride, now I can finish the table by converting my moles of zinc chloride to grams of zinc chloride, which is my goal. In both cases, I want grams of zinc chloride. Yes? No. No. Yeah. Do not do any math. Don't do any reducing. Don't do anything. Do you? You know the excess reactions by looking at it? Because you have less of this, right? Right. Yes. This is the last one. Here's the problem. 1, I won't give you partial credit if you make a math error. Okay? If you try to do it in your head or reduce, you'll go from 4 points, making a math error, getting 3 points, to 0 points. You didn't show your proper work. And not only I, the college board will too. They'll be like, well, the answer answer is wrong. No points for the answer. The process is wrong. No 2 points for the process. I don't even do this. When I'm preparing solutions for you or chemicals for you, I don't skip steps either. There's no reason to. It's like, well, that saved me 15 seconds. Okay. So now we got moles, we gotta get to grams. How many grams are in a mole of zinc chloride?
136.
136? 137?
136.
136? Okay. We're gonna go with 136 grams of zinc chloride. 136 grams of zinc chloride. Now my last unit is grams of zinc chloride. Is that what I'm looking for? Yay, now I can do some math. This one's going to be 3.5 multiplied by 136 divided by 2. And this one's going to be 2.3 multiplied by 136 divided by nothing. 3, 2, 1. This feels like 240.
238.
238? Okay. And this feels like almost 300.
312.8.
How much?
312.8.
312? More than 300. Okay. Grams of zinc chloride. Grams of zinc chloride. All right. So I've got two numbers. I add them together, right? No. A lot of people wanted to add the two numbers together while you were doing the limiting reactant simulation. You don't add the two together. What this tells you is this. If hydrochloric acid is limiting, I'm going to make 238 grams of zinc chloride. If zinc is limiting, I'm going to make 312 grams of zinc chloride. Which one's limiting?
The hydrochloric acid.
So this is our limiting reactant. That makes this the excess reactant. And if we take the limiting reactant, and this is our correct answer. 238 grams of zinc chloride. Now, if you wanted to know, and you frequently will, next level, challenge mode. If you wanted to know how much of the excess you used, you would replace your product with, you'd replace your, you do a third T chart. You'd start with HCl, then you'd replace your product with your zinc. And that would tell you how much zinc you actually had to use. Does this make sense?
Yeah.
So the smaller one's always limiting.
The thing that makes the smallest product
Yeah.
is limiting. Yeah.
Can you show an example of that?
Yes. Okay. So, guys, the question was, can you show an example of that? The answer is yes. Should I do it?
Yes.
All right. So now we're going to take the same exercise, and instead of converting to zinc chloride, we're going to convert to zinc. Make sense? So this is going to be the amount of zinc we had to use. So it's a 2-to-1 ratio. So that would mean we would need 3.5 over 2 moles of zinc. That's how many moles of zinc we'd use. Does that make sense? So 3.5 over 2 is 1.8. 1.75. So 1.8 moles. And of the 2.3 moles, this is what we did in the simulation, we had 2.3 moles. We only used 1.8 of it. That means there's going to be a half a mole of zinc sitting there in the bottom of the beaker. Make sense?
Yep.
All right. Give me a thumbs up if you're ready to do one all on your own. Okay.
Oh, yeah.
Put your hands up and wave it around if you have questions. All right. This one is for you.
You're doing it better. Nobody's stopping you.
The chemical reaction looks like this. This is a thermite. Aluminum plus Fe2O3 yields iron plus, iron plus aluminum oxide. And we'll chuck a 2 up here and a 2 right there. So this one is for you, all on your own. Baby birds leaving the nest.
Bug, maybe a nest. Practically the same thing.
Wait,
Sea salt and vinegar. You like this next table.
you got wave check.